Okay, so as I see it, I'm the only one today advocating for fully homomorphic encryption. So I will take upon me to try to show you exactly where we are in fully homomorphic encryption, and my talk will be a little bit more technical. So I will provide you with more details about where we are in homomorphic encryption and why originally it was hard to apply homomorphic encryption to neural networks, and why this, we believe, is a revolution in the making. So first of all, what the problem is. So, sorry about that. Yeah, I think it's better. All right. So first of all, my talk is about machine learning as a service. So you can find commercially available a number of services in your cloud that provide you with inference. That is, you have a trained neural network, a trained cognitive model that is available through an API, for instance. And basically, you have a user and you have Mr. Cloud Inc., whatever company this is, that provides access to the like some kind of Oracle access to the trained network. So it's an object that has been trained before, and now it's running. We're running what we call inference, which is evaluating the neural network on user inputs, and it usually runs on GPUs. And so this is something that is booming at the moment. And so basically, the user has, I don't know, in the most simple of cases, you have pictures, and you want to know whether it's a dog or a cat, as Nigel was describing this earlier. And so you send the data over, the inference is run on the GPUs in the cloud, and then you get the prediction back. Or whatever the result of the inference is. It can be a prediction if you want to predict probabilities out of financial data, it can be classification on images, videos, whatever. So the problem, of course, is whenever the user has sensitive data to send to the cloud, then Mr. Cloud Inc. will learn about that data. And of course, that's like the elephant in the room for machine learning as a service. And even worse than that, the result of the inference itself can be confidential, can be highly sensitive, because it contains information that can be highly sensitive. And it's very easy to convince people that this is indeed a big problem. Essentially, when we work on data coming from the, I don't know, some ELF data has been collected, or if you think about DNA sequencing and genomics, but it can be a lot of other things, like financial data, or even, you know, I don't know, like case-solving data. You know, now machine learning is used to try to solve cases, like automatically. Like you give all the details, all the information you have about a case, and there's a neural network that tries to come up with an explanation, what was the truth, what happened exactly. And so there is a lot of PII in there, personally identifiable information, which is like personal data. And so it's, if assuming that everything is delegated to a cloud service, then it's a problem to also protect that kind of data. So the very nice idea with homomorphic encryption is, so why not encrypting the data in the first place? Then you upload this encrypted data to the cloud service, and now inference, the neural network, the evaluation of the model is done homomorphically over encrypted data. So it's a very natural approach, and there's if you can do that, then you're kind of protecting the user's privacy and data confidentiality. And so the user is now going to learn the network, but then the cloud operator will not learn the data either. So this is like a game-changing scenario. And so of course the user will generate keys for himself or herself, encrypt the data, send that, give the public key for evaluation to the cloud service, and then decrypt the result with his own key. So there's a big motivation for trying to apply homomorphic encryption to neural networks. So homomorphic encryption, so at the very beginning, so it remained like an open problem for 3 decades. It was like the holy grail of cryptography, one of the holy grails in cryptography. There was a lot of discussions about its very existence. Some people even tried to come up with the possibility results, so it couldn't exist. And it wasn't until about a decade ago that Gthe showed the first candidate scheme for fully homomorphic encryption. So at the time, if you want to look at it that way, basically you encrypt bits, so you split your data into bits, which is something you can do very easily by encoding everything into bits. And you encode your computation into a circuit, like a Boolean circuit. And and the thing is, with the first schemes, the first generation of FHE schemes, then given the encryption of 2 bits, you could get the encryption of the sum mod 2 of these 2 bits, so the XOR, or multiply the 2 bits. But there was a huge difference between adding 2 bits and multiplying 2 bits. And the first operation was pretty fast, well, faster actually than multiplication. And multiplication would be like a pain in the ass, would be like an operation that would be much more costly. But the nice thing is that actually that solves the problem of existence. You can compute like an arbitrary circuit and get an encrypted result. But there was another notion that was introduced at that moment. So when you use probabilistic public key encryption, there's always some randomness in there to provide some what we call semantic security. And there is also some randomness in homomorphic ciphertext. And the noise behaves in certain ways when you perform homomorphic evaluations. So basically, if you compute the sum of 2 encrypted bits, then the noise in the resulting ciphertext will be approximately the same in terms of size as the input noises. But if you multiply 2 bits, then the size of the noise doubles, which means noise suddenly becomes a problem. And so after a while, you cannot go on performing a homomorphic evaluation because there's too much noise, and if the noise exceeds some bound, then the result is not decryptable anymore. So you're just computing, on garbage information, and it doesn't make any sense. So at the time, Gthe, but I think it was an idea that was even that existed before that. The idea here is to apply bootstrapping, what we call bootstrapping, which is you take the decryption circuit and you apply it on a ciphertext using an homomorphically encrypted secret key, and so you get the encryption of the encryption of X as input, you get the encryption of X as output, but in the meantime you kind of destroy the noise in the input ciphertext, and you get a new ciphertext with some kind of nominal noise, which only depends on the nature of the decryption circuit. So now you have more room for the noise, so you can go on with homomorphic evaluations and until you reach the upper limit, and you do a bootstrapping again, and you go on and on like that. So it was the only way to make homomorphic encryption scale invariant, that is, being able to apply that to arbitrary functions, is to apply bootstrappings regularly in the circuit, so that you can go through. But the problem is, of course, bootstrapping originally was an operation that was extremely slow, so very, very dispersive. And because of this difference in nature between additions and multiplications, suddenly it became clear that depending on the circuit and how multiplications appear in your Boolean circuit, you might have to basically to take more to process the circuit more. Well, you would need more time to process that circuit because you would need to use bootstrapping a lot more. So the notion of multiplicative depth, which is in the circuit the path that contains the most multiplications, it's really the bottleneck in the circuit, because the noise is going to double every time in size across that path, but that path belongs to the computations, so you have to go through. And so And so if the noise grows like that, then you have two approaches. So in one approach, you perform a bootstrap at each and every operation. So you have a circuit, and you bootstrap every time you do an homomorphic operation. So if you do it like that, you can go on forever. If you're given a circuit and you want to compute the function, then you do it like this. But if suddenly there is something else that requires to be done, a new circuit that is chosen like dynamically, you have nominal ciphertext, so you can go on and now evaluate this new computation. And so this is like the scaling variant, the real fully homomorphic encryption vision of computations. And you have the homomorphic encryption approach, which is completely different, which is, okay, I have to go through this circuit there. So what I'm going to do is I'm going to create enough room, enough space for the noise to grow, so that I can do no bootstrapping at all. I will go through the circuit. And then at the end here, I will have ciphertext that are with a noise level that is maximal. If I would do one more computation, things would become undecryptable. But at least if I stop there, then I can send that back to the user. It will be able to decrypt, and it will be valid. So this is an approach that avoids the use of bootstrapping. But of course, if the circuit is very complex, you have a high multiplicative depth, then of course the parameters to maintain a certain security level could explode. It's a polynomial explosion, but in practice you can make it like that. It's going to destroy your performances. So neural networks. So I guess, how many of you know what a neural network is? I guess everyone, right? Yeah, okay. How many of you have played with programming frameworks and generated trained models? 1, 2, 5? Yeah, half a dozen people. Okay, that's good. So for the others, so a neural network is some kind of it's a cognitive model. So it's an object. It's like a formal object. You could represent it and play with it in code. But it's something that does two things. First, there is a training phase. It's going to learn things based on the data set, the training data set. And then when it's trained, you can apply it, and this is called inference. You just apply it on new data, and you get a result of the result of that. It can be a prediction or a classification or whatever. And the basic computing object in a neural network is a neuron. So a neuron does only two things. So it's a very simple computational entity. It takes as input a vector of real values that we call activations. And there is a vector of weights, which are also real values. And the neuron just computes the scalar product between the weight vector and the activation vector. And then to get something that we call a multisum. And there could be a bias in there, which is also a real value. And then once this is computed, it applies some kind of nonlinear function to it. So it is usual to take like logistic sigmoids, or hyperbolic tangent, or the sine function sometimes, or ReLU, which is rectified linear, so it's the max of 0 and y. There are other examples, but this will be the most popular in that area. So a neuron works like that. And then at the level of the neural network, you combine layers. So you take the neurons, you put them into layers, but they can be connected in different ways. So there are several topological ingredients in neural networks. And the most obvious one is dense layers, fully connected layers. So you have, like this, you have a layer of neurons, and on the neurons on the next layer are going simply to be connected to all the other neurons in the preceding layer. So you can see that the multisum, so you have actually weight matrix and a bias vector, and then usually you use the same function in the same activation function in all the neurons. So you map that function on the vector that you get. And of course, this is a layer that is learnable. All the weights and biases in there will change during training, will be adapted. And the gradient descent, the backpropagation algorithm will change them so as to minimize the cost function, and then which means that basically the model is learning. So there are learnable parameters in there. You can also apply convolutions, which amounts to have something that is a bit less connected. But basically, when you go from layer L to L plus 1, the multisum in the red neuron over there is computed as a scalar product of activations taken from a window here. And with weights that are the same size. So you do the scalar product between this window and what we call the kernel here, and you get a result. And then you switch, you will screen the window across the entire image. So of course there are a few details in there. You might want to start, you might want to first pad your image with zeros, for instance, or so there are a few tricks, but if you take my word for it, so it's basically something that is heavily used for image recognition and computer vision in general. And so what is learnable in there is the kernel. So what is not learnable is dimensions of the window. Of course, this is a 2D example, but you can be in like any highly dimensional space. And a layer, a convolutional layer, can be a combination of several convolutions with different kernels. So this is something that really appears very often. And then you have other topological ingredients, like average pooling and max pooling. So again, it's a question of a window that screens the activations in the layer, and that takes the maximum value, for instance, in the window, or averages out all the values in the window. So of course, this is not learnable. This is an example of a topological ingredient in the network that is not going to evolve during the training. And also you can change dimensions. Like if you have a layer, you can reorganize things in there so that you can lose dimensions and flatten out everything. Or lose one dimension or several dimensions. And then we also have operations that are some kind of a multivariate. It's not, so they're not local, they're to each and every neuron, but they're actually across the entire layer of neurons. So the softmax is an example of that. So if you have activations here, they're the vector of real values, you're going to exponentiate each value, and then you get a new vector, and you divide it by the sum of the exponentiated values. So that gives you, so it's kind of a trick so that you end up with something which, a vector, which all coefficients sum to 1, so you can interpret that as a probability vector, a vector of probabilities. So it's very useful for classification. Basically, we'll have the probability that it's a dog, that it's a cat, that it's a giraffe, that it's an elephant, and so on. And then the sum will be 1, so you can classify like that. So the softmax operation, what we call auto-regularization, which is taking the vector, dividing it by its norm, its auto-norm, or its L1 norm, or there's even elastic regularization, which is like a combination of both. So now back to homomorphic encryption. So how do we mix, how can we actually do the homomorphic inference? So the first thing is that if you look at it at a very high level, so each neuron is going to do a linear combination of inputs, and then you have to go through this activation function. So the good news is, well, something is linear, and fully homomorphic encryption loves linear, because this is the efficient part of it. Everything is very efficient. It's addition or multiplication with known public constants. So that's very efficient as well. It's very close to an addition. So it's a multi-addition, and this is very efficient regardless of the technical choices you make and which particular mechanism you want to use. But apart from that, if you look at the other part, which is the activation function, well, this function is meant to be highly nonlinear. Otherwise, if you take a linear function, the network is not going to converge during training because the network is going to be fully linear. So it's not going to learn anything. So it's something that is highly nonlinear. But as I told you before, morphic encryption doesn't like that. So you don't know what to do. So the first approach was, oh yeah, and there's another problem, which is you have to deal with real values. But you know, normally a neural network is robust towards approximation. So you could encode your real values into discretized values and work with that. So if you take my word for it, and if you dig into the details, yeah, you'll see that things could work out. So Krypton X actually was a couple of years ago. It was the first attempt to solve that problem of going through the activation function homomorphically. And Krypton X is coming from Microsoft research people, and they're using the library which is SEAL, which is based on second generation FHE, where the noise grows linearly instead of exponentially, but you still have this problem of noise growth. But in the somewhat homomorphic encryption vision, you prepare all the parameters to leave some room to the noise and you let it grow through the network. So you don't want to do any bootstrapping in that vision. And so they said, okay, what is the simplest function that we can use that is non-linear and that is the less costly to do homomorphically? And the answer was, obviously, was the square function. So what they did is they just got rid of the activation function and they put a square function in there, and they said, oh yeah, we can do that efficiently, which is true. And then what is amazing is that it changes the definition of what a neural network is. But why not? You could work with networks in that class of networks and see how it goes. And so they did that, and they changed the training procedure accordingly. And they trained toy examples, and they saw that the accuracy was actually pretty decent. So amusingly enough, even if you make a change like that, you get an accuracy that is decent. It's not that bad. So that's what they did. But they had no solution for layer-wide operation, like applying the softmax, regularization, max pooling. Everything in there was kind of out of the question. So they just replaced max pooling in their toy examples. In the topology, they replaced max pooling by average pooling. So there is a loss of accuracy, of course, if you do things like that, but that's what they did at the time. And of course, so you have to go through a number of layers. Every time you have to perform a square. So you can set up parameters at the beginning so that you can go through, and the output of the network will be, the ciphertext will be fully, will contain a maximal noise, but you can still decrypt them. So that was the Krypton X approach. And so there's a demo. If you go to Microsoft in Redmond, they will do the demo. It takes roughly 5 minutes on the MNIST use case. So the MNIST dataset is basically images of handwritten digits between 0 and 9. And you have to classify the images to say, okay, this is 7, this is 3, this is 0. And so it's usually a problem of reference in machine learning arena. So they did a toy network that actually does that with pretty good accuracy. But it takes like 5 minutes if you want to, even though it's pretty small, it takes 5 minutes to evaluate it homomorphically. So, and then, so 2 years ago as well, what we like to call the 4th generation of FHE came about. So it's called Taurus FHE, TFHE, because so it simplifies a lot of things, and actually it's a simplification and generalization of the preceding generations. And so it's symmetric in the sense that you have a key to encrypt and decrypt, which is secret, and the public key is the one to carry out evaluations. Plaintext are bits in the nominal version of TFHE, but you can extend that to integers. And they can support all the binary gates. And the very nice thing with Taurus FHE is that the bootstrapping is super fast, like a few tens of milliseconds. So there is a very nice open source implementation on GitHub, and we have the pleasure to have Ilaria with us today, who is one of the authors of TFHE. And we think it's a game-changing approach in homomorphic encryption. because it simplifies a lot of things, and you bootstrap every operation. So things really become scaling invariant. You're not going to spend 3 minutes just to bootstrap a ciphertext. It's just a few tens of milliseconds, so you can go on forever. So what we did, and we published results in Crypto this year, is actually we took TFHE and we adapted TFHE specifically for neural networks. And so in that paper, it was about a certain class of neural networks called binarized neural networks, where all the weights are actually not real values, but they are plus and minus ones. And the activations are not real values, but plus and minus ones. And when you do the scalar, product, you end up with an integer, and you extract its sign. So either it's plus, the output of the neuron is either +1 or -1. So it's the same function. But still, you can learn, and it's known in the machine learning arena that you can solve problems with BNNs, binarized neural networks. It's not as efficient, but at least using a fork of TFHE and adapting a few things, we showed that it would be much faster than Krypton X. And in the meantime, since we did that, we actually found plenty of other tricks. It's a big bag of tricks now. So we know how to speed up the bootstrap procedure of TFHE. We have a new bootstrap procedure which is called noise reduce, which does something else. And also we use a feature which is you can program the bootstrap procedure in TFHE-like schemes. So basically, once you've done, so I won't get into the details here, but it doesn't matter, but once you're done the scalar multiplication, so you encode your activations as on the torus, 0, 1. After that, you perform homomorphically the multi-addition with the weight vector, which is there. But when you do so, the noise of the resulting ciphertext will grow. Its variance will be multiplied by some information. And so you have to go through the bootstrap procedure to reduce the noise so that you can go on to the next layer and so on and so forth. But so the bootstrap will reduce the variance and you can go through the entire network. But the very nice thing is that actually the bootstrap procedure can be programmed so that if we program it, we can put any univariate function in there. And for free, for no extra cost. So that means while you're reducing the noise, you can apply on the multi-addition here, on the multi-sum, you can apply any function of your liking. So you can do much better than Krypton X. We can put our activation function just in there. And it's not going to be approximated, or it will be the untouched original function. And so for no extra cost. So when you do that, it means you can solve the problem perfectly for neurons. And but the problem is the weights have to be integers. So you're given a neural network, you have real valued integers, real valued activations. So the first time you will do is take all your weights there, multiply them by 1000, round that up, and in the function here you will divide by the 1000 factor so that it's equivalent. But you can put whatever function of your liking here. So we can support ReLU, hyperbolic tangent, sigmoids, we can do that neuron per neuron, and it's going to be efficient. And we found plenty of other tricks, so we know also how to do the max pooling. If you want to compute the max, then you do the difference. You bootstrap with the function max of 0, comma dot. And then you add this, and you bootstrap again with identity. So it's going to work. And we also have leads how to solve the softmax problem and regularization to do that homomorphically and efficiently at the same time. So in the end, if we summarize, we have something that supports homomorphically like whatever topology, whatever neural network is given to us. And this is something Krypton X couldn't do because they had to have their own definition of what a neural network is, to go through their own training with their own data. But here, what we can do is just take a pre-trained neural network and and just convert it into its homomorphic equivalent and run that homomorphically. So we don't have to take care about the training phase. Somebody is going to give us, under NDA for instance, his own neural network, his own model, pre-trained, and we're capable of converting that into an homomorphic equivalent and to perform inference homomorphically. And so these are game changers for the industry, we think. And also we're working on a first version of the technology, and we see that there are plenty of speed-ups, that tricks at the arithmetic level that you can do. So just to mention, so where Krypton X would take 5 to 6 minutes, we had a few examples developed with toy networks solving the MNIST use case that would run in 1 to 2 seconds, depending on the number of neurons. And actually we have improved over these results in the meantime. And so the business offer that we are creating now is to allow Mr. Cloud Inc., who runs machine learning as a service, to migrate from an inference service in the clear into a homomorphic inference service. And to be able to give that as a new service or a new option to his customers. And so basically what we're building now, the technology that we're building, is some kind of compiler that takes as input a neural network. Basically, all the weights and biases and the topology, everything is given to us under NDA. We press the button. Right now, it's not automated at all. I mean, a little bit, but it strips. You have to run that manually. And in the end, we get some software that runs on GPUs, written in PTX code, which is assembly language for GPUs, and which is portable across all NVIDIA generations. And plus utilities that Mr. Cloud Inc. can give to its users to generate keys and encrypt and decrypt. But we're still figuring out the business model really, because we could as well have our own cloud infrastructure and convert pre-trained models given to us by other people and provide a homomorphic inference service. But in the two cases, it's a different product, it's a different service, it's a different bunch of customers, it's a different message. So, but we're still trying to figure this out. So, but there are plenty of things yet to be resolved. So we'd like to switch to GPUs. So far our demonstrator only works on CPUs. And of course what would be absolutely tremendous, another game changer, would be able to do the training on encrypted data. And of course, so what we see that you need other encryption techniques to do that. The bag of tricks that we've developed is not good enough to support that. So we have to extend that in multiple ways to be able to support training homomorphically. But that's a very nice thing to explore in the future. So, and one thing over MPC that you don't have with MPC, but you do have with homomorphic encryption, is that with MPC you have to assume that, so everything is split into shares at a high level view, but if everybody colludes, then it's over, right? With FHE, you're the only one having the key, and the rest of the universe can collude together. It doesn't matter. You're the only one who has the key to decrypt the result. So I was just trying to to advocate for homomorphic encryption. But of course, MPC and homomorphic encryption are two approaches of high interest for the industry. We see now that things are changing and evolving quickly, and I hope that more and more people will be adopting one or the other in the future. Thanks.